Have you ever looked at a still lake? From a distance, its surface seems perfectly flat and smooth. It looks like a single, unbroken sheet of glass. You could imagine sliding across it without a single bump. This is how we usually think about the universe itself. We see space and time as a smooth, continuous background. It's the stage where everything happens. Stars are born, planets spin, and galaxies collide on this grand cosmic canvas. Our everyday experience tells us that space is just empty, and time flows forward like a steady river, never stopping, never changing its pace. This smooth, predictable stage is the world described by Einstein's famous theories. But what if that smoothness is just an illusion? What if, just like the lake, the closer you look, the more complex it becomes? If you were to zoom in on that lake's surface, you would see it's not smooth at all. You'd find tiny ripples, waves, and constant motion. The water molecules are always jiggling, bumping into each other in a chaotic dance. This is a much messier, more energetic reality than the calm picture you see from far away. Scientists now believe that the fabric of spacetime itself might be just like that lake. From our large-scale perspective, it appears calm and orderly. But if we could zoom in to an unbelievably small scale, we might find a completely different universe waiting for us. This idea challenges our most basic assumptions about reality. It suggests that the quiet, empty void of space is actually a seething, bubbling cauldron of activity. This hidden reality is so small and so energetic that it's completely invisible to us and our most powerful instruments. So, we have two incredible theories. General relativity, Einstein's masterpiece, perfectly describes the big stuff: planets, stars, galaxies, and the graceful curvature of spacetime. Then we have quantum mechanics, which perfectly describes the small stuff: atoms, electrons, and the weird fuzzy rules of the subatomic world. The trouble starts when you try to make them work together. Think about the heart of a black hole. Here, an immense amount of mass is crushed down into an infinitesimally small point. When you try to combine them, they don't just disagree, they give you complete nonsense. The maths spits out impossible answers, like infinities, which tells physicists that something is fundamentally wrong. To understand where this quantum foam might be hiding, we need to talk about scale. You can measure things in meters, then centimeters, then millimeters. With a microscope, you can see things measured in micrometers like a single cell. But the world of quantum foam exists on a scale so small it makes an atom look as big as a galaxy. This is the Planck scale, the absolute smallest possible unit of measurement in the universe. The Planck length is about 1.6 times 10 to the minus 35th meters. That's a decimal point, followed by 34 zeros, and then a 16. To put that in perspective, if you were to scale up a single atom to be the size of the entire known universe, the Planck length would be about the height of a single tree. It is the pixel of reality, the point at which the smooth image of space breaks down into its fundamental components. For quantum foam, that champion was the brilliant and eccentric American physicist, John Archibald Wheeler. Wheeler was a true giant of 20th century physics. He reasoned that if you look at space-time on the very smallest scales, the quantum fluctuations wouldn't just be some minor background noise. The energy fluctuations would become so violent that they would completely overwhelm the smooth geometry of space-time, tearing it apart. In a landmark 1955 paper, he painted a vivid picture of this subatomic realm. He described it as a multiply-connected foam-like structure, a chaotic sea where space and time are ill-defined. Imagine you're flying high above the ocean in an airplane. From your vantage point, the surface of the water looks incredibly smooth and flat, almost like a sheet of blue glass, stretching all the way to the horizon. Now, imagine you descend from the airplane and hover just a few feet above the water in a helicopter. The picture changes completely. You can now see that the surface is not smooth at all. Imagine you dive into the water. Now you are completely surrounded by the chaos. Bubbles are forming and popping all around you. Currents are pushing and pulling you in different directions. The water is a churning, energetic medium. This is the world of quantum foam at the Planck scale. It's not just that space-time has ripples on its surface, it's that space-time is the ripples. There is no calm water underneath. The chaos goes all the way down. The very fabric of reality at this fundamental level is a seething, violent, and unpredictable froth of pure energy and geometry in constant flux. Let's look more closely at the bubbles in this quantum foam. These aren't bubbles of air in water, but bubbles of pure energy and warped geometry. In the quantum foam, the energy of these virtual particles is so immense that it has a profound effect on spacetime itself. Some physicists believe that these violent fluctuations could be so extreme that they momentarily rip tiny holes in the fabric of spacetime. These fleeting tunnels could connect one point in space to another, or even one moment in time to another. They are microscopic temporary wormholes. They wouldn't be big enough for a spaceship or even an atom to travel through. They would be just 1 Planck length across and last for only 1 Planck time. Since we can't build a galaxy-sized microscope, scientists have turned the universe itself into a giant laboratory. One of the most promising methods is to study gamma-ray bursts. These are colossal explosions that unleash a torrent of high-energy light. This light travels across billions of light-years to reach our telescopes. The idea is that over this immense journey, the light's path is subtly affected by the foamy texture of space-time, kind of like light getting blurry as it passes through murky water. So astronomers use instruments like the Fermi Gamma-Ray Space Telescope to watch for gamma-ray bursts, hoping to see if the high-energy photons arrive a fraction of a second later than the low-energy ones. Other physicists are trying to find evidence on a much smaller scale, right here on Earth. These tabletop experiments use incredibly precise instruments called laser interferometers. Some scientists think these sensitive devices could also detect the noise from the quantum foam. Imagine for a moment that one of these experiments succeeds. The discovery of quantum foam would be more than just another scientific breakthrough. It would be a fundamental rewriting of our understanding of reality. It would be the first ever piece of experimental evidence for a theory of quantum gravity, the holy grail of modern physics. It would prove that space-time is not the smooth, continuous background we thought it was, but a granular, dynamic, and probabilistic entity. This confirmation would instantly open doors to solving some of the universe's most profound mysteries. The problem of singularities in black holes and at the Big Bang would have a solution. We began our journey on the surface of a seemingly calm lake, a perfect metaphor for our everyday view of the universe. But we learned that this placid surface is an illusion. We took a deep dive, plunging beneath the calm facade into a world of unimaginable chaos and energy. We journeyed down to the Planck scale, the absolute smallest unit of reality, a realm so tiny it makes an atom look as big as a galaxy, and there we found the churning, bubbling chaos of quantum foam. The quantum foam, first envisioned by the great John Wheeler, is the theoretical battleground where these two realities must finally be reconciled into a single, unified theory of everything. We are like cosmic detectives, slowly piecing together the story of a universe that is far more intricate and surprising than it appears. Every non-detection, every new piece of data helps us to refine our ideas and close the net. So the next time you look up at the night sky, or ponder the simple emptiness of the space between things, remember the chaos that might lie beneath. Remember the seething, bubbling foam of potential, the place where space and time are born and reborn every instant. The universe has not given up all its secrets. In fact, we may have only just begun to scratch the surface. The greatest discoveries may still be waiting for us in that turbulent, invisible realm just beyond our sight. The story of quantum foam is a reminder to us all to stay curious, to keep asking questions, and to never stop exploring the magnificent, endless frontier of reality.